Good afternoon, everyone, and welcome to the EGU2016 General Assembly and to our first press conference. I'm Barbara Ferreira. For those of you who don't know me, I'm the EGU Media and Communications Manager, and I'll be your host at the Press Center this week. And with me, I have 3 press assistants, and you are welcome to approach any of us if you need anything, or if you want to book one of the 4 interview rooms we have available. We have organized 8 press conferences for you this week, which include a period for questions following the presentations from the speakers, and the journalists watching remotely can use the chat feature to ask questions to the panelists. Press releases or other documents that relate to each of the press conferences are uploaded online at media.egu.eu/documents. And they are uploaded every morning. There are new documents relating to the various press conferences. And the first one we have this week is on impacts and costs of natural hazards, and we have 3 people in the panel. The first speaker is Giovanni Forzieri. He's a researcher at the European Commission Joint Research Center at the Institute for Environment and Sustainability Climate Risk Management Unit in Italy. James Daniel is a researcher at the Geophysical Institute and Center for Disaster Management and Risk Reduction Technology at the Karlsruhe Institute of Technology in Germany. And Mitja Brilli is a professor at the Faculty of Civil and Geodetic Engineering at the University of Ljubljana in Slovenia. And I'll hand over to our speakers. They'll give their presentations, and then we'll open the floor for questions. Thank you very much.
Thank you for the introduction. I'm Giovanni Forzieri. I present the study Multi-Hazard Assessment in Europe Under Climate Change. This work has been developed in collaboration with many other research institutions, supported by the DG Clima Action. Our results, recently published in Climatic Change, show that Europe will see a progressive and very strong increase in overall climate hazard, with a prominent spatial gradient towards southwestern regions. We also see a strong increase in heat waves, droughts, especially in south, and also coastal flooding. Key hotspots emerge along coastlines and floodplains. Europe is expected to face major impacts due to climate change. Risk to society and environment will be largely connected to extreme events due to their disproportionate rise compared to the corresponding changes in climatological averages. However, to date, there is a lack of a comprehensive picture on how multiple climate extremes will evolve in Europe along the 21st century. So we try to fill this gap. This difficulty in the current literature is mostly related to the fact that each hazard is characterized by very different processes and characteristics. For instance, heat waves and cold waves are usually expressed in terms of degrees, floods, in terms of extension of flooded areas or water depth, droughts in terms of number of consecutive dry days or river low flows. So we try to fill this gap and to identify those geographical regions in Europe that are expected to be more exposed to multiple climate extremes in the next decades. I also want to emphasize that this study should not be confused to a risk assessment study. Risk assessment implies the combination of 3 components: weather and climate events, so the hazard component, exposure, so people living in a certain place or assets, and vulnerability, so the susceptibility of people or assets to a given hazard. In this study, we only focus on the hazard component that remains a key component of the risk assessment. In our approach, we collected a set of 7 climate hazards, some of the most dangerous for Europe, including heat and cold waves, droughts, river and coastal floods, windstorm, and wildfires. For each of these hazards, we generated an ensemble of possible simulations, all consistent with the A1B climate scenario, which predicts a 2-degree global warming by 2050. Our simulations run up to the end of the century, and this allows to quantify the uncertainty of our results, because we generate a very very large number of hazard scenarios, up to 840. Our approach focuses on the changes in frequency of extreme events. So we analyze a certain event in the today climate, and we see in the future how often this will occur. And for instance, in this figure, we see the situation for a certain area in the south of Europe, specifically for droughts. Along the x-axis, you can see the baseline return period of a certain event. Over the y-axis, you see the corresponding changes in future frequency. With the different color lines, we see the different scenarios. So green is 2020s, blue 2050s, red 2080s. The different dimension of the circles reflect the uncertainty of our results. So if we focus, for instance, on a current 100-year event, we can see how often this will change in the future scenarios. So for instance, these events will occur every 12 years in 2020s, 5 years, every 5 years in 2050s, and every 2.5 years in 2080s. So in this specific example, we see that this region, this area, will experience a strong increase in drought hazard. So this approach allows to make different hazards comparable and to combine them in a consistent and quantitative way. So here I show some results expressed in terms of changes in overall climate hazard. So in this case, this figure shows the evolution in time and space of the fraction of area that is expected to be every year exposed to at least one hazard on the left, at least two hazards in the middle, and at least three hazards on the right, with the current 100-year event. In other words, where we have red areas, this means that this area will experience at least 1, 2, or 3, depending on the column, hazard that every year, an hazard that actually is occurring every 100 years. So there is a strong increase in frequency of this hazard. For clarity, I also put in colored label the overall climate hazard of the today climate. So we can see a strong increase in overall climate hazard over the whole Europe, with also a prominent spatial gradient towards southwestern regions. This is mostly related to those hazards closely linked to the rises in temperature, like heat waves, droughts, and wildfires. Looking at the changes in multiple climate hazards, in this figure we see the evolution in time and space of the number of hazards with a relative increase in frequency over a certain threshold. In this case, over 20% on the left, over 100% in the middle, and over 1000% on the right, compared to the today climate. So in other words, red areas in this case reflect those regions that are expected to manifest an increase in hazard up to 4 hazards with a relative increase over a certain threshold. In this case, we see that those areas more exposed are mostly along coastlines and flood plains, where floods and windstorms will be critical when in combination with other hazards. And this is very relevant because those areas are very often those more populated and also critical from an economic point of view. Thank you.
Good afternoon. Today I'm going to talk to you about the economic costs of natural disasters globally from 1900 through to 2015 and talk about historic losses as well as then a thing called normalized losses. We've looked at this for many different types of natural disasters and we've looked at this globally. So over the last 14 years and really since I've been a child, I've been collecting loss data, developing a huge database around the world. And if we look at direct economic costs from natural disasters, we see that what happens is that it is increasing. So there's a total increase in terms of absolute losses. Since 1900 to 2015, flood has shown over a third of all losses. Sorry, I'll just go back. Storm, in recent times, however, has overtaken flood, causing 30% of all losses. And what we see is that flood still holds, from 1900 to 2015, about 40% of losses. Storm, about 20% of losses. Earthquake, about 27% of losses. However, relative to the global value of all buildings and infrastructure, this value is actually decreasing. So although absolute economic costs in terms of 2015 US dollars are increasing, relative to the total value of the globe, which is increasing faster than this, we have a relative decrease. Now, this is globally. We're not talking about country by country, we're talking about global trends. In terms of the highest percentage of historic costs per country, if we take all of the costs of each disaster from 1900 to 2015 and sum them in 2015 US dollars, we see these on this graph here. So we see each country is very different. Through Africa, in a lot of countries, drought and temperature effects have shown the highest losses. Whereas in Australia, USA, storm has the highest losses. Now with flood and storm, it's extremely difficult to split sometimes the effects of wind and the effects of flooding. And we've tried to do this in a way that we look back into the records and try to associate an economic loss with flood and an economic loss with storm or storm surge. But still, there's a huge amount of uncertainty in doing this, because the split of whether it was a wind loss and then a flood comes with rainfall, it is quite difficult. So the Natural Disasters Database, it's been built since 2003, and it's one of the largest disaster socio-economic loss databases globally. Now, what sets it apart is that there, firstly, is a lot more events, about 35,000 after 1900 and about 53,000 in total. What's very different is that we search in a lot of different languages globally. So we've used over 90 languages so far around the world to develop this, and about 30,000 sources. So it's a labor of love. We also have, so during my PhD, I tried to develop socioeconomic metric databases, so population, GDP, the value of buildings through time, to try and explain some of the trends in these losses. And what is very different to our database is that we provide a range of results, not just one value saying that, okay, the earthquake yesterday in Ecuador caused 800 million. We say that there was a range of losses from the government because it's very difficult to know ever exactly what the value is. And this helps then develop rapid loss estimates post-disaster. Now, if we were to take every single disaster and look at it in terms of 2015 economy, now just changing it using the value of buildings. So the value of buildings in 1950 versus the value of buildings to 2015, we take that ratio and multiply it by the losses that we saw in 2015 US dollars in 1950. What we see is a decrease globally in terms of these trends. And this is mostly due to improved flood protection measures in China and Japan. Now, in other countries, we see increasing flood trends. So maybe in Thailand and places like this, there is an increasing flood trend. But overall, the losses seem to be decreasing in terms of this capital stock again, so in terms of this value of buildings. In terms of the cost of deaths, well, deaths over time, they're very, very different. Over all time, flood again has the highest amount of deaths with 51%, earthquake 43% in recent times. In terms of absolute numbers, total deaths are reasonably constant. However, again, relative to the population of the globe, we are decreasing, which means we're doing better. In terms of relative number, however, versus the global deaths per year, because we're having decreasing child mortality and increasing life expectancy, what happens is versus the global deaths per year, we have virtually a constant trend. So we are doing better for disasters, but we maybe could be doing more. So in conclusion, over 8 million deaths and about 7 trillion US dollars, depending on which metric you use for adjusting dollar terms for measuring worth, have been seen since 1900. Absolute losses are increasing globally. Now, I stress again globally. Each country has difference, and when we go down to a regional scale or a sub-country level, it's even more muddled. However, losses are decreasing globally versus the value of the world's infrastructure. Deaths are reasonably constant versus global death rate, but decreasing versus population. And in terms of normalized losses, we do see a decreasing trend globally for flood, but some countries increase. In terms of storm surge, droughts, we see increasing trends, and for earthquake, it's reasonably constant or no trend. Again, on a country level, there can be no trend sometimes in these losses. So this CatDat database is used for various things: historic data, trends, and it's also used as part of a rapid disaster loss model. So the database is dynamic. Each year it changes and losses come out. So we also have a rapid loss estimate associated with it for each disaster that comes mostly for geophysical. So for the Ecuador quake yesterday, we had different values that come out. And so this comes out on our websites around the world. And so thank you very much. Let's get yours up.
Okay. Thank you very much. I will present the master degree thesis of our students, Treo Rangel from Mexico. He studied flood risk master management under Erasmus Mundus, including also UNESCO University IG from Delft, Technical University from Dresden, Technical University from Barcelona, and University of Ljubljana. Why he analyze and study this subject? Simply, real estate evaluation, okay, it's very complex, but it's also very important driving force in urban development. Finally, the real estate market is something which in the past pushed us to heavily regulate our rivers, and now we have some trouble with them. Okay. On the other side, also, the real estate owner give a very strong obstacle against to publishing of natural hazard maps, because they are afraid if the real estate will be on the natural hazard map, then the value will drop down and so on. On the other side, these real estate owners are highly motivated stakeholders. Whatever you would like to organize, some conference, a workshop, whatever related to the floods, the real estate owners which are in the hazard area has great interest to be involved and discussed. And finally, in Ljubljana, real estate owner organized NGO to make a pressure on the local authority to make better protection against the floods and so on. Then what we found during the research, there is extraordinary lack of data and lack of knowledge. If you talk about the lack of data, more or less analyses are finished on the data which we collect from United States and not from other places. And that was also one of the problem which has candidate, because he would like to collect data from Mexico, from United States, and from Slovenia. And finally, we don't present, but he couldn't find the data from Mexico. They are some kind of really obstacle there. And then here is another impact is attraction of the riverfront. Riverfront, first line close to the river, has is real estate some additional attraction, and it's more expensive than the real estate out of the riverfront. And other side, this is part which is very strong exposed to the floods. And then is the question, due to floods, the value decrease, due to the riverfront value increase, and so on. And we try to look on this. Okay. Here are what we found in literature. It is some analysis how much after the floods real estate value dropped down, and the percentage evaluate quite widely and strongly, and ask for additional analysis. But more or less everywhere is some drop down, up to even 60 to 70%, which is really a lot. It means practically that house is destroyed. Okay, here are his two case studies. First one is in Boulder, Colorado, who really suffered in floods in year 2013. It was 100-year return period of flood. And if you look more carefully, you will see that more or less the values in the floodplain are higher than outside of floodplain. Really, trend of increase of real estate value are on the same. Really, flood has no any impact of the situation, but what we found looking on the number of the contracts after the floods dropped down. That means the market reaction of the market is not to decrease the real estate value, but decrease the number of contracts, because the real estate owner doesn't like to sold the property on the lower level for the lower value. It is some characteristic of the United States real estate market, which maybe ask for some additional explanation, and it's characteristic of the real estate market in United States, which is really market. The people has a lot of property and so on. Here are results from Ljubljana. Thanks to the government who start to collect the data for tax paying and so on, we collect our geodetic survey, collect very good data from year 2009 and collect data in the period also the floods, because in year 2010 we have very serious also in the magnitude about 100-year return period of floods. And the reaction of the market was not so clear. Also, if we look on the number of the contracts also doesn't change so much. What we found, and what is very interesting, is these changes between year 2013 and 2014, because in year 2014 we have also some floods. But what we can recognize here, that real estate market recognized additional value of real estate in the riverfront, close to the river. That is our hypothesis, and we would like to collect the data from year 2015 and then maybe publish all together. Simply looking on the data, there is no so significant impact. In the United States, just drop down number of the contracts. And in Slovenia, we make a questionnaire with the NGO of the people who are flooded and organize themselves to make a political pressure on the town authority. And they, related to the questionnaire, they express the figure of about drop down of 10%. They evaluate that the value of the real estate, because the floods, should be lower up to 10%. That is final results. Thank you very much.
Thank you very much for your presentations. We'll now open the floor for questions. If you have any questions, please state your name and affiliation and who the question is for. Does anyone here in the room have questions?
Hi, Jonathan Amos, the BBC. James, I mean, obviously you're counting the money and stuff, but frequency of the events themselves, are you able to see in that data whether these events themselves are actually increasing over time?
So if I bring up this slide here, this is the number of disasters we have defined through a certain economic threshold and a certain fatality threshold. Now, the problem comes that when we go back in time, this is not complete. So we may have reports, say, from 1930 or 1940 on floods and storms that just have never come into the database. For earthquake, however, what we've really worked hard in the last 5 or 6 years for earthquake and volcano to make it complete. And what we see when we go through earthquake globally is that the green line there are reasonably constant. So the amount of damaging events, although we have an increasing population globally that's more spread out as well, these events were still happening back in 1900 and affecting maybe a smaller amount. So it might have only caused $100,000 in damage, where it may cause 2 million today, where there's a lot more people exposed, but it was still enough to cause an event to come into the database. So that's really the only test that we have of this sort of hypothesis.
Right, because I mean, the interesting question is whether you see a climate signal in there.
Yeah, and that's where I'll probably hand you across to Giovanni. Yeah, because unfortunately with this loss data, we do not see it. I mean, it's not that we don't see one, but it's that there's no trend. So we can't give a trend. So it's more up to the hazard modeling on a regional scale.
Yeah, what I didn't show an analysis of the recent trends in the changes in frequency of climate-related hazards, but what we observed with other studies is that there is an increase in frequency of most of the hazards related to climate change. For instance, prominently heat waves and also droughts for some regions. In the specific case of Europe, for instance, droughts will increase prominently in the southwestern of Europe. Heat wave over the whole Europe. And sorry, when I talk about droughts, I'm talking about streamflow droughts. So only the component of the hydrological cycle. So in that case, droughts will increase in the south and will decrease in the north. It's let's say a positive effect of the climate change. For the case of cold waves, for instance, they will disappear almost completely over the whole Europe as effect of the progressive increasing in temperature. So depending on the hazards, we may have an increase or a decrease in frequency, even in the last 3 decades. So just focusing on the observed trends.
But you expect most of the hazards or the increase in frequency mostly to south of Europe, southwest of Europe.
Yeah.
And the reason for that is just latitude.
Because those regions are more exposed to effects of increasing temperature, even if temperature will increase also in the north of Europe, maybe in proportion even more. But those regions in the south are more prone to these kind of hazards. Yeah.
Hi, thank you. Marlo Hood with Agence France Presse. A question for James and Giovanni, if I may. Why is your estimate of $7 trillion damage towards the low end of your range?
Yes.
I'll answer that.
Yep. So it's towards the end of the range because there are different metrics that you can use to bring forward a value from, say, 1950 into 2015 dollars. You can use a consumer price index or inflation rate, GDP deflator. You could also use a construction cost index, which is maybe more relatable to the building damage that you may see for that dollar value of a building in 1950 versus 2015. And so if we just use CPI GDP deflator for each country, we get about 6.5 to 7 trillion. Whereas if we start using a building cost index combined with unskilled wage index, which is a good proxy for the labor that's applied after an event, then we get up towards the higher end. So 10 trillion, 12 trillion. 14 trillion is a country-based value where you've got a combination of unskilled wage, you've got some project escalation indices in there, some building cost data in there as well.
So the 7 trillion is more a CPI.
It's more a CPI adjustment, exactly,
and
on each
just,
country.
Sort of journalist kind of question.
No.
The 7 trillion figure, is that something new that is emerging from your studies? Are there any other estimates of sort of total 20th century? Or
I haven't seen one out there totally in this way because most people up until now have adjusted using just a US CPI for all countries and other sort of adjustment indices. So this is where I believe that my database or our database is a difference to other databases where we adjust the values hopefully better or more realistically, having a range there. Yep.
And a quick question for Giovanni, if I may. I think it was fairly well established that the Mediterranean basin, Southern Europe, was most exposed to heat waves, drought. So that's clearly not new. But what did you learn that might be new in terms of looking at all the different sources of hazards together? Is there some sort of multiplier effect or compound effect that emerged in your analysis? Thank you.
Analyzing how multiple hazards may combine together is something that sorry, is not has been done before, because as I was saying before, when we talk about risk assessment, all the impacts are quantified in terms of euros or population affected. In such case, the impacts of different hazards can be compared together, as in this study, for instance. When we analyze the hazard component, when every hazard is characterized by different metrics, it's hard to assess if an hazard is experiencing a larger impact compared to other ones. That's this is one of the main novelty of our study in terms of methodological approach. In terms of results, is expressed in the indices we show in a synthetic way the combination of the hazards together. If I can just briefly to, thank you. In this case, for instance, this is an index called overall exposure index, overall exposure index. Yeah, is the result of the combination of all the 7 hazards we have, and in a certain sense, this give you in each area of Europe the proportion, the fraction of that territory that is expected to be every year exposed to a certain number of hazards, independently from what kind of hazards. So, and this is something that has not been presented in previous studies. And also this figure provides a complementary information, because this counts the number of hazards that are expected to be over a certain threshold. So in this case, red hotspots are those areas that are expected to be exposed to multiple hazards. So probably adaptation strategies should be developed in a way that accounts for different typologies of impacts.
Are there any additional questions from here in the room? They can, yes. If
that should be fine.
Okay with you.
May I just say something? Yep. So the losses that we saw today were direct costs. So this is not including indirect effects of losses. So an example would be the Tohoku earthquake. So that had, from our assessment at the time of the event, it was 335 billion in direct losses. But indirect losses are things like a loss that is associated not by the direct effect of the event, but sort of a supply chain loss to a production, say in Japan. And these are of the order of around about the 150 billion mark for Tohoku. Of course, in 2015 US dollars, now Tohoku has gone way down because the Japanese economy has gone down in terms of US dollars. So that 335 is today 230 billion. So, yep.
If I can add briefly, this work has been accepted in climatic change. It should be available online by the end of the week, I think. So
just one last point, really. I guess. I mean, there was a report recently which said air pollution kills 6 million people a year annually. It's not a natural hazard.
No. Very interestingly, I've got another presentation on death rates around the world that we've looked at. So for disaster death rates versus other types of deaths. And yes, there's some very interesting trends in different countries around. So I'd be happy to share with you these slides.
Are there?
Andy Coglan, New Science. Your talk, I mean, obviously things are getting much worse in terms of absolute events, but you seem to be saying that we're kind of getting better at protecting ourselves. Is that correct?
We are getting better in protecting ourselves. Certain countries are, at least. Some countries have not done as much as they probably should have, but in certain countries, say China, from the big 1954 flood event, they have now put in a lot of prevention measures along the Yangtze, and we can clearly say that the 1998 events and other events that we've seen in China have had reduced losses compared to what they would have been without these measures. But there are other places in the world that is concentrating.
So here's the interesting thing. We've heard from Giovanni that these events are going to go up in frequency. So will there come a crossover point where we start to do worse again?
I think we'll probably see that in 20 years. We may be sitting here again, and we've seen the trend maybe go the other way, but we'll have to see.
Right. Okay. Thanks.
Thank you. Are there any other questions? Well, if there are no more questions, you are welcome to approach any of our 3 speakers for interviews. And like I said, there are interview rooms available. And that's it for today. This is our only press conference. We have 3 more tomorrow, starting with one on civilizational resilience and collapse. It's not as depressing as it sounds. And that's at 9 a.m. And this afternoon, there is a union session on NASA, ESA, and EGU if you want to join that. Thank you very much. Thank you very much to our speakers. Thanks.